Hello everyone, discuss contest 23. Unfortunately, nobody solved it almost, so um, there will be no your solutions to discuss, but we will discuss it anyway. Probably someone will solve it later. So if you're watching this and didn't solve the contest, just stop now, solve the contest, and then watch, because it's kind of doesn't make sense to watch these discussions before you actually solve the problems. Uh, let's go to discussion. So again, I pre-recorded myself solving all the tasks, so let's watch. Problem 1, very straightforward, nothing interesting, just implement what's written in the problem statement. So we have a square, and we need to check if this square contains a big cross. Yeah, so we have to check that all elements on both diagonals are the same, and all other elements are the same, and they're different. So we have two characters. One character belongs to both diagonals, and other character belongs to all other positions. Many ways to do it. I just do it like this. So I try to think as little as possible when I implement solutions like this. So I keep my, you know, uh, my brain energy for future. But yeah, it usually turns out to be something like this, some messy code, which is not very readable. But if it works, then okay. So that's it. So what I'm doing, I'm not even having this square read before. I read it and immediately check. So I read it and I maintain these two characters. So I maintain characters from first two positions. Okay, let's stop here. Boom, can you stop there? So I keep characters from first two positions. See, so it's top left corner and the next one. Yeah, so one of them will be A, another will be B. If they are the same, immediately false. Then I just check all other characters. So if it belongs to diagonal, here I check if it belongs to diagonal, it should be A. If it's not, it should be B. Just check. If anything is not where it should be, OK is immediately false, and then I check that OK is true. Nothing really to talk about in this problem. That's it. So that's the whole code, and nothing, no interesting ideas in this problem. Just implement what's given. Let's go to problem B. Oh, problem B is also very not very fun today. So yeah. So we just need to check if it's possible to make triangle out of given four numbers. So we're given four numbers. We need to pick three and try to build a triangle. And you can build a triangle if maximum out of three numbers is less than sum of two previous numbers. Yeah. So you can build a triangle if one number is too large, if it is greater than the sum of two other numbers. So that's what I check. So I know, okay, I do it cheating way. So I sort all these numbers. And so if you want to build triangle, you kind of want to use three consecutive numbers in the sorted order. So I sort these four numbers, and there are two triples. Yes, numbers 0, 1, and 2, and numbers 1, 2, and 3. So I checked both of them just in simple. If you have n numbers, it will be more fun, but if you have four numbers, I just implement it like this. That's it. Again, first problems today are not very interesting. So we will move to interesting problems in the end, but first problems are just for start. Let's go to problem C. In problem C, you need to count how many hexagons you have on distance less or equal than given number n. And what I'm doing here, I'm trying to guess the formula. So number n is large. So I first checked number n is large. So I cannot make a single loop and count all these numbers. Yes, I need, basically, they asked me to guess the formula in this problem. Yeah. And how do you guess the formula? Many ways to do it. Here what I'm doing, I kind of assume this formula would be a quadratic polynomial. Because of reasons. No, because, okay, so how can you guess that number is a quadratic polynomial? In this problem, I see that this number is sum of my arithmetical progression, you see? So in every layer you have 0, then you have, how much? 6, then you have 12. So this number is 1, okay, so 1. So you have 1, 1 plus 6, 1 plus 6 plus 12, then we have 1 plus 6 plus 12 plus 18 and so on. So every number is sum of the arithmetical progression, and arithmetical progression is sum of arithmetical progression is quadratic polynomial. So that's why. But again, if you solve many problems like this, you just at some point you just see that something must be a quadratical polynomial because of how it looks. Yeah. So this function must be a quadratical polynomial. The only question is to find the coefficients of this polynomial, and it's enough to have 3 values. So here I will just guess it. Yeah. So I write down 3 values of this quadratic polynomial here, and it is enough to get the coefficients. You can do it just by writing linear equations, or you can just guess it like I did. So you know, the third coefficient c is 1 because value of 0 is 1. Okay, it's easy way to find coefficient c in these quadratic equations. Then you have basically linear equation of 2 parameters, and I solve it by looking at them. Yeah. Again, there are many ways to solve linear equations. Just pick the one which works for you in this problem. So in this problem, I just guessed basically these values all. Okay, it's not guessing. It's this case more like, let's say, educational guess. So I just see which values you should put. That's it. So that's it. So I guess the formula, check if it works, and then submit. That's it. So that's problem C. Okay, maybe a little bit more fun, because so if you never did something like this, that's how you do it. Yeah. So you need to find the formula. You guess the formula is quadratic polynomial. You find this quadratic polynomial, write formula, and that's it. Sometimes you have problems like this, and sometimes you have, so here it's not very fun because the whole problem is guess the formula. Sometimes you have something like this in the middle of the problem, of the solution. Yeah. So you do something, and then in the middle you guess the polynomial. Yeah. So it's just sometimes it's more fun. Here it's just one step. Let's go to problem D. In problem D, we have some type of puzzle where we have, let me draw the picture. So we have some elements in a circle like this, and one island is empty, all others contain something. So we have some, what is it, 3, 1, 2, and 4. And we can move them by only using this empty slot. Yeah. So in one action, we can take one of these items, and move it to this empty slot. So we can take this, move it here. Then we can take this, move it here. Yeah. And if you play a little, you need to check if it's possible to make one configuration from another configuration. Yeah. And if you play with it a little bit, you can kind of see that the configuration kind of doesn't change. Yeah. So we just move these elements in circles. So we have like in this direction or in other direction. So the order of these elements doesn't change. Yeah. We just move this empty spot along the circle. So what we need to check? So we need to check if the order of these elements is the same if we consider all cyclic shifts. Yeah. So if we ignore this empty slot, look only at these elements like 1, 3, 4, and 2. Yeah. And you have in another configuration, you have something like 4, 2, 1, and 3. Yeah. You need to check that you have the same cyclic array. And okay, many ways to do it. I will do it like this. Since all elements are unique, you can do it like this. You can just move element 1 in the first position. So here is already in the first position. Here I will take element 1 and move it to the first position by applying cyclic shift. So I will take all these elements and move them here. So I have 1, 3, 4, 2. Yeah. And just check that I have the same configuration. Yeah. So basically what we're doing, we for every, we have 2 states, we need to check that they are kind of the same state. Yeah. And you do it by moving all states to some canonical state. Yeah. So in both states, I make a rotation of this array, which moves element 1 to the first position. Okay? This is unique rotation because all elements are unique. So, and so you just need to check that these two rotations are the same. So that's what I'm doing here. Okay, I spent too much time thinking how do you implement it in more beautiful. So I kind of want to make pretty code in this problem so I can show, because I know you will read it. It turns out to be not that beautiful as I expected, but yeah, you'll see. So for both these configurations, I need to read this configuration without this 0. So okay, I will do it like this. I will just not put a 0. So I will put all elements except 0. See. And then rotate it by moving element 1 to the first position. Here, yes, I double check that all elements are different here. So I find element 1, yeah, see, and just move it to the first position, make it rotate. Rotate is just operation which does what you make cyclic shift of the array. Okay. That's it. In the end, I will just check that I have same configurations. That's it. That's problem D. Yeah. Again, it requires some thinking, it requires some careful implementation, but nice problem actually. No, not very difficult, I would say, but no, kind of nice. Okay. Okay, now we go to problem E. Problem E, I hate problems like this. I'm not sure why people put these problems in contests, but sometimes they do. Yeah. So sometimes judges just don't have any good problem nearby. So they and you need to have some problem in the contest. So people keep occupied writing some code. So you get problem like this. So nothing interesting in this problem. Just pure implementation. You just read all this text and implement exactly what's written in problem 6. So I don't know what tells about this problem. So maybe the only challenge with the problem is to carefully implement without any mistakes. And okay, here try to Google if it's possible to split string by space in C++. Okay, sometimes I try to educate myself, so I try to find if there is a nice way to split a string. I didn't find anything, so I just write it like I usually do. So I read the whole text in a single line, then go from left to right. If I see space, I copy what's before this space as a single word, like this. Yeah. So this code basically splits this string into words. See. Yeah, nothing very fancy, but yeah, it works. And now what I will do, I will find type for each word. Yeah. So we have words of basically 6 different types. Yeah. And I will enumerate them with integers. So I'll say types will be 1, 2, and 3, and the same feminine types will be -1, -2, -3. Okay. So because it will be easier to check in the end. Yes. So try to again. I try to simplify problem for myself. So boom. Basically, you need to encode 2 parameters. Yes, type of the word and the gender of the word. Yeah. So I enumerate. So value identifies the type of the word, and the sign of this integer identifies the gender of the word. Yeah. So I can use single integer to encode 2 parameters. Nothing really interesting there. So if it didn't fall in any of these 6 patterns, I immediately say no. If I have only one word, I say yes. So it's written in the middle here. So sentence may contain only one word. Okay, so here. Yes, there is example for this. No, example fails in the second configuration. Tricky problem. Here I check that all have the same sign. And finally, in the end, I will check the final thing. Yeah? So I will find this only word of type 2. Yeah. So I'm finding word of type 2, and then check that everything before has type 1, everything after has type 3. Okay, I decided not to break, I just check it right here. Yeah. So I check all the previous words that they have type 1. Hate problems like this actually. But again, like I told you many times, you don't need to love problems. Yes, just solve them. Yeah, you have this problem, you need to solve it. Just solve it and move forward. Check everything. Check everything. Submit. That's it. Not that much code actually. Yeah. So if you implement carefully, you have this 70 lines of code. And how much time do we spend for this problem? Okay. Well, not that much time spent. Yes. So it can be implemented pretty fast, and not that much code. So it's not pretty problem, but it's okay problem. Yes. Just implement it, solve it, and that's it. Let's go to interesting problem. Problem F. Oh, problem F is fun. Problem F is actually a constructive problem about graphs. Not that many of them. Okay, this not that often you can see constructive problem about graph nowadays. So we need to build a graph. We need to build a graph, very specific graph. We need to build graph with two combinatorial paths from vertex A to B and from vertex C to D. What's interesting? So okay, like this. So show you. My first thought was that you can do it like this. You can make a cycle. Yeah. So you can make A to B. Okay. What was my way of thinking? So okay, let's see. So let's do it like this. So make A to B. No, okay. Again, question is to do it using the minimal number of edges. So the parameter K. So they give you maximal number of edges you can use. But it's obvious that if you do it with minimal number of edges, you can just check, yes. So let's try to do it with minimal number of edges. Kind of make sense that n minus 1 edge is not enough. Yeah. If you have only n minus 1 edges, then you have only single path, and you need to have two paths from one A to B and from C to D. Yeah. So if it's possible to do with n edges, and first I thought it's actually possible, you can do it like this. You can make a cycle, yeah, and you can make like nodes A to B nearby, yeah. So then you have this path from A to B here, yeah, and also make some C and D here, yeah. Then you have path from C to D here. Yeah? So n edges should be enough. But this will not work because there is no road between A and B. See here. So there is no road between A and B, so you can't have edge AB, and you can't have edge CD. So your solution is actually different. Let's go back. I actually draw a nice picture here, I believe. Okay, still testing. Okay. So I'm just starting to draw some, not I don't want to say pictures, but just draw something which to visualize what's happening. So I must have some path from A to B. So I have Hamiltonian path from A to B. Yes. In this Hamiltonian path, I must have all the nodes, including C and D. So C and D are somewhere in the middle of this path. See? They cannot be nearby because there is no edge from C to D. Yeah. So I have situation like this. I have A, then somewhere in the middle I have C something D, see, and then in the end I have B. So that's how the first path looks like. First path looks something like this. First of all, if n equals 4, you just can't build path like this because you need this extra node between C and D. If n equals 4, you cannot have this extra node between C and D, C in the middle. So n equals 4, it is immediately impossible. Let's think about n equals 5. Now I'm just trying to build answers for small values of n and see how do they look like. and try to build a general solution out of these small examples. Sometimes it doesn't work. Sometimes it works, like here. So here, if n equals 5, then the first path looks like this. Easy, yes? So how to find the second path? No, second path should go from C to D, yes? And from C I can go to A, then where I can go? So it's not that many choices, yes? From A I can't go to B because there is no H, A, B. I can't go to D because I need to finish in D, yeah? So the only way to go from A is to this middle node, yes? And then it's kind of, so this is how you build the second path, yeah? Ta-da! Okay, so my graph looks like this. And then I think, okay, but I can do the same for any number of n. So for any number of n, I can build graph of n plus 1 edges with 2 cycles like this, which will give me 2 different Hamiltonian paths from A to B and from C to D. Okay, I don't know if I draw this picture. It says let's draw this picture now. So you do it like this. So again, you have answer for 5 looks like this. I have A something B and C something D. Yeah. So you have path from A to B like this, and path from C to D like this. Yeah. And if you have any extra nodes, you can just put them here. That's it. So this is how you build a graph of n plus 1 edges. Question is if it is possible to do it with n edges. It turns out it's impossible. I believe did I draw a picture for this? I just started So it's impossible because of the following reason. Okay, I believe many ways to prove it. I proved it like this. So if you have A, again, picture looks like this. C, then you have something, then you have D, then you have, and then you have B. So the first path always looks like this. Let's look at the second path. So second path contains n minus 1 edges. Yeah. So what is the maximal edges from this path I can utilize in the second path? Let's see. So I have this node C. This node C in the second path, so it's C to D, only can have one edge connected to it. Yeah. So one of these edges is not in the second path. Some of them. Same for node D. One of these edges is not in the second path. For example, this one. Yeah. So from this first path, I need to throw away. I have n minus 1 edges here. Then I need to remove these 2 edges at least and add 2 another edges. Yeah. So total number of edges will be at least n minus 1 plus another 2 edges. Yeah. So it should be at least n plus 1. You see? Okay. So no, yeah, many ways to prove it, I believe. So or you can just believe. You can just believe that if number of nodes equal to n, then like the most interesting thing you can construct this cycle, and you can just check that cycle doesn't work. Yeah. Okay, that's it. So let's go. So you check that one cycle is not enough. So you need at least 2 cycles. If you have 2 cycles, you need at least n plus 1 edges. Yeah, and n plus 1 is enough because you build the construction. Okay, here I try to. Okay, I did it for a long time. Okay, my final solution works like so. So how to implement this? I will implement just like this. So I will just build this in array like this. Tricky part is they give me these values A, B, C, and D. I need to put them in correct positions. So I will build this first path, just put A, B, and C, and D in correct positions, and fill all other empty spots with all the rest nodes. Yeah. So okay, not very pretty code, but you'll see. It's actually pretty okay. So again, I put this array 8, so this will be my first path. Yeah. I put node. I read these nodes in positions 0 and -1, 1 and 3. So I put A, B, C, and D in incorrect positions. Yeah. Then I fill the rest with all unused elements. So I mark all used elements. So I make this array Z of used elements. And here I will just go from left to right. And if I see empty spot, I fill it with unused element. Like this, because why not? Yeah. So this J is some unused element. I skip all used elements here. Yeah. Pick the minimal unused element and put it in these positions. So I go for empty positions and just every time I take the minimal unused element. Not the best code in the world, but it works. Yeah. Okay, and it will be my first path. Now the second path will be just the same as the first one, but I need to reverse these two parts. Yeah. So I will reverse first two elements, basically swap A and C, and reverse this part between B and D. Yeah. See? So here I have C. You see AC, then this one extra node, then part from D to B. This is D, this is B. See? So I reversed these two elements, and I reversed these four elements. So I go from path from A to B, path from C to D. Okay, let's go problem G. Problem G is fun. Problem G is really fun. Actually, last two problems are very fun. So problem G, you have a tree, and you have some beavers in this tree. What you need to do is you walk along this tree. Every time you move to a node, you decrease number of beavers by 1. And the question is, you need to traverse the tree, then move back to initial node. So you start in node and finish in the same node. And yes, and you want to maximize number of beavers you eat in this process. Fun problem. Okay, first, so what I'm doing first, I try to visualize the example. So they give me example. It's not very trivial. Sometimes they just give you very trivial example. It doesn't look very trivial. So thank you, judges, for this opportunity. So I just draw this example and just play with it, see what's going on. So I better understand what's going on in this problem. So you have this starting node 4, and you go there. So I need to go. So for example, I need to go to the. I can go to node 3, eat this beaver, then go back, eat this beaver. Yeah. Then I can go here and go here. Okay. Already by here I notice that again we traverse the tree, and we start from the root, and we need to finish in the root. Yeah. What does it mean? It means we traverse each node in both directions. Yeah. So if I go somewhere, I then need to go back. Yeah. So every edge will be traversed in both directions equal amount of times. Yeah. So I go there, go back, then go there, then go back. So for every node, for every edge, I will go in both directions same amount of times. That's actually an important observation. What does it mean? So if I have, so again, imagine you have some edge in the graph, like from node X to node Y. Yeah. And if I go here and decrease this number by 1, then at some point later, I need to go back. Yeah. And then I decrease this number by 1. So basically what we're doing, we can pick the edge, traverse it in both directions, And when we do this, we decrease both numbers by 1. Yeah. So if we decide to use this edge, we will decrease both numbers in the ends by 1. This is important observation. Yeah. So this is how the system works. So we pick some edges which we will traverse, and if we traverse this edge, we decrease both the ends by the same amount. Okay, here I'm just playing and thinking about it. So the second example doesn't look interesting, so I skipped it. So sometimes I visualize both examples. Here, the second example is not fun, so I think first is enough. Okay, here I'm starting to think. It looks like so by now, it kinda looks like greedy algorithm. Why it looks like greedy algorithms? Because of many similar problems can be solved using greedy algorithm. For example, what problems you can solve in the trees using greedy algorithm? Maximal matching in a tree can be solved using greedy algorithm. Minimal vertex cover in a tree can be solved using greedy algorithm, and so on. So I think that this problem also can be solved using some kind of greedy algorithm. For example, if I solve the following problem, if I don't think about the path, if I'm solving, so I'm allowed to take the edge. So when I take the edge, I decrease numbers in both ends. Yeah. So I'm allowed to pick some edges some number of times. Let me show you. So you have the tree. In every node you have some number. Let's say 5, 3, 1, 4, 2. Let's say 3, 1, 6, 4, 5. Too many. Let's say enough. So then imagine these are your numbers. Yeah. So every time, so you pick the edge. So when you add this edge to your path, you decrease both numbers by 1. Yeah. So every node. So basically, this number is maximal degree of this node. Yeah? So I will put some edges to my path. Yeah. Every time I add edge to my path, I decrease both numbers by 1. So I can put as many as 3 node edges here and 5 nodes here. And if it is the problem you solve, so the problem is to pick as many, so to draw as many edges as possible, but in such a way that the degree of each node is at most this. So this number is the maximal degree of this node. And you need to put as many edges as possible. Then you definitely can solve it using greedy algorithm. You just go from bottom to top, from leaves. Yeah. So here you have number 5. So you can connect 5 edges here. Yeah. But the parent has number 3. Yeah. You only can connect this number to this node because it's leaf. Yeah. Leaf can only be connected to its parent. Yeah. So you have 5 here, 5 here. So you can put only 3 edges here. So I can put 3 edges. And now this node is done, this node is done. Now I can put 1 edge. So here we have 1, so I have boom, 1 here. Now here I have 4. Minus 1. So I have 3 left. And my parent has 2. I can add 2 edges here. And then so on. So you have 1 edge here, 2 more edges here, and 4 edges here. Yeah. So if you're allowed to put any edges and just one maximized number of edges you take, that's how you do it. You just go from bottom to top and greedily put as edges. It's basically the same as when you make maximal matching. Maximal matching is basically the same problem, but all nodes have value 1. Yeah, this is just generalization of maximal matching problem. Okay, hope you're still with me. Now, our problem is actually different. So it's similar to this, but it's different. What is the difference? Difference is, so this is not correct path. So my path should be connected. Yeah, so you see, so if I pick these edges, I cannot traverse these red edges. So again, so imagine you have only these red edges, yeah? You cannot traverse this path because it's not connected, yeah? And this property of being connected actually limiting what we can do. For example, in this node, so if number is here is 3, okay, 3. So imagine number here is 3. I need to connect this node to the parent at least. So it stay connected, yeah? So I need to connect this node to parent, and now I can only connect 2 children, yeah? So I'm limited of number of children I can connect to this node. How does it change our greedy algorithm? No, easily actually. So what we need to do? So we need to take so if we are limited in number of children we can connect, we connect only the children which give us the maximal number of edges. So for each child, I will count number of edges this child can give me if I connect it. And if I am limited in number of children I can connect the biggest children. Okay, hope it's clear enough. Now I will just start implementing. Yeah. So again, I'm not very okay at this point when I'm implementing this. I have some picture in mind, yeah, of what I'm implementing. It's picturing not very clear, so I kind of feel what I need to implement, but not exactly. So I will finalize all the details in process. So what I'm doing here, I kind of want to so my recursive function should return 2 values. So when I finish working with subtree, I return number of edges I take from this subtree plus what's left in the root. So after I do it, let me know. So you take some subtree, you have some so you have some node X. Yeah. So you go here and try to work with this subtree X. Yeah. In this subtree, you go somewhere, visit something here, go somewhere here, something here, and then go back to node X. Yeah. So what I'm interested in? I'm interested in the maximal number of edges I can take. So the first parameter. So I return pair A and B. Yeah. So this first parameter will be maximal number of edges I can visit in this subtree. And the second parameter will be the the residual degree of this node X. So this node X had some number. So let's put some number here. Some number 5, for example. Then I connected to, let's say, 3 children. Something like this. I connect to 3 children. Plus I connected to the parent. Okay, I didn't connect. Okay, I didn't count this. So I take this number node. I connect to 3 parents, to 3 children, but the number is 5. So I'm allowed to connect 2 more edges. So this second parameter will be equal to 2. So it will be number written in this node minus number of edges I already connected. So what this number means? It number means I can make 2 edges here. So this number is number of edges I can put from my parent to this node. Okay, hope clear enough. Normal DFS, just normal DFS. So here I recursively go to every child, call recursive procedure, and just accumulate all these values in some array. Now I will sort it in decreasing order because I want to take it from. So if I don't have enough, if I can't visit all the children, I will visit only the largest ones. Yeah? Rename variables. Okay, so now here I check if I can visit all the children. So t is number of children I can visit. Yeah. So if I am the root, I can visit k children. If I am not the root, I can visit at most k minus 1 children. Yes, because I have one edge to the parent, and plus I can use at most kx minus 1. Yeah. So t is maximal number of children I can visit. Now here I check if I can visit all the children. Then what I will do, I will visit all the children, take all the edges, plus some other edges to the child cells. Yeah. So okay, what I'm doing here. Okay. Here I will finally do something. So I will calculate. So I need to calculate total number of extra edges I can add to my children. So I have already some edges from the subtrees, plus I will add these extra edges to my children directly. Okay. Too slow. Come on. It's not easy problem. I think in the middle. So like I told you, so I don't have very clear picture of what I'm doing. Yeah. So I modify it in process. Okay. So here total number of edges will be calculated like this. Okay. Okay. Yeah. So now t is number of extra edges I can add to my children. Now, okay. So I cannot add more edges than my children allow me. So in this SB, I calculate total number of children I can make from my node to my children, from X to children of X. Yeah. So T here, okay, is maximal number of edges to my children I can make. Hope it's clear enough. Now I calculate total number of edges. Total number of edges will be SA is just sum from all my subtrees, plus T is number of extra edges to my children. Yeah. Now B is the number of children I can put from my element to its parent. It's so kx is total number of edges minus T is number of edges I already put. Yeah. So this is I can put B edges more from this element to its parent. Hope it's clear enough. Nice problem. A lot of complications here. I love it. Here, if I have not enough, if value is not enough to visit all the children, I pick only maximal children. So I sort them in decreasing order and pick T first elements from this array. That's it. So here I have 3. Yeah. That's just because I calculate maximal number of edges, but every edge give me 2 beavers when I go down, when I go up. Yeah. So I just multiply by 2 and that's it. Nice problem. Not very. It's. I would say this is very unusual for problem 3. So normally I would expect some dynamic programming here or something like this, but it's actually kind of greedy solution. Not that often you have some interesting greedy problems on trees. Love it. So let's go to problem H, last problem for today. Okay, last problem is about maximal increase in sequence. So you have sequence, it is periodical. So it has period of size n repeated t times. And what we need to do is to find the maximal increase in sequence in this long sequence. Nice problem. So what here I check that check the constraints. Constraints are interesting. First of all, you need to answer k queries. So you have multiple queries, but like number of queries is like 10. Usually it's happening not because you need some online algorithm, something like this. So in some problems you give multiple queries. It means you need some pre-calculation then to answer queries fast. Yes. Here it's most probably not. So when they give you like 10 queries, it's usually because authors want you to make fast solution. So they don't want you to fit some non-optimal solution like n square and square root of n solution or even n square solution. So they just want you to not trying any cheating stuff. Yeah. So they want you to make kind of optimal solution, fast solution. Yeah. Yeah, I think that happened because they tried some n square solution, and in C++, C++ is very fast. So they tried an n square solution and it worked. So they decided we put 10 tests, so any n square solutions will fail. Yeah, that's nice constraint. Yeah, I don't like problem with constraints like this, but sometimes people do it. Yeah, I don't like them because it's kind of unnatural. So it's very unnatural constraint. Yeah, so they promised you that the product of n and maximal value of b is no more than this. It basically means that either you have a small array or you have any small values, not both. Yeah, so you can have big array with big values. Okay, so two reasons why I don't problem like this, because first, it's very unnatural to have constraints like this. It's not what you do. Sometimes you have natural constraints like this. Sometimes it happens that so just in real problems, sometimes you have constraints like this. It's actually true. But I still don't like it. They doesn't look very interesting. So you only find this constraint when you read up to here, some in the middle of the input component. Not very fun. And another reason is that these constraints usually kind of force you to think in specific direction. So when you think about algorithm, you want algorithm to utilize this constraint, right? So you think about algorithm which has kind of time complexity of n multiplied by max b, because you know this value is small, so you want this product in your time complexity. So you think, okay, what can it be if I have these two? Basically, okay, if I have two loops, one loop of size this, another loop of size this, what can it be? So you think in this specific direction, it will kind of guide you to a solution. It's not very fun, I would say. No, okay, but again, this specific problem is kind of fun because it utilizes interesting concepts. I will show you. Okay, skip it. Let me draw you a better picture. Okay, so this problem is about maximal increase in sequences, subsequences. Yeah. So what do we know about maximal increase in subsequences? How do you usually calculate? So let's start from the beginning. So when you have a problem like this, first you just remember everything you know about the object. Yeah. So how do you normally find maximal increase in subsequence? You do it using dynamic programming. Yeah. So you have array A, you go from left to right. Okay, simple dynamic programming. Goes from left to right, picks the element, yeah, some element in position I, and picks some previous element with position j, yeah, such that aj is less than ai. Good. So that's how you. And then when you find elements like this, then you calculate d of I is the length of the maximal subsequence with this last element, yeah. So it's just maximum of all these values dj plus 1, yeah, for all elements j such that aj is less than ai and j is less than I. Yeah? So go in those previous elements which are less than mine, yeah, and calculate maximum of these values. Ta-da! So that's how you do it in n squared time complexity. We obviously cannot do it like this because n squared is too much. Yeah. Let's move forward. So what else can we do? So we can do some type of so another way to calculate longest square sequence is to do it like this. So let's change it. So instead of here for every element I calculate the length of maximal sequence. You can inverse this, yeah. So you can do it like this. So you can calculate array D of, let's say D of X. Yeah, and it will, so D of X will be subsequence of length X. So for every length, we will remember something about the best subsequence of this length. Yeah, and usually you do it like this. You go from left to right, and you for every subsequence of X elements. So if you have subsequence, so imagine you have subsequence of X elements. Yeah. So if you want to be able to extend it, you want this last element to be minimal possible. Yeah. So usually, again, it's popular algorithm. I just explained briefly because it's very popular algorithm of finding maximal increasing sequences. Yeah? So you go from left to right, and you maintain for each length the minimal last element of subsequence of size X. Something like this, yeah. Okay, and then when you take the next element here, so if you go to position I, take element I, you want to update this array, yeah. So you can add this element to subsequence of length X if my element is greater than this, yeah. So if D of X is less than element AI, then I can update you can update T of X plus 1, yes, as minimum of previous value dx plus 1 and my element AI. Yeah. Something like this. Yeah. And normally you do it in n log n time just by seeing you can only update one element. So you can look at your array D. So these elements are less than AI. This element are greater or equal than AI. Yeah. So you pick this. So you pick this element. So this is the maximal element less than AI. Yeah. So you can update only these elements. So this is the only element you can update. And you find it using binary search and update only this element and continue. So you iterate all these elements, find this position using binary search, update it, and in n log n time complexity, we have the algorithm which finds maximal increasing subsequence. Again, this is classical algorithm of finding maximal increase subsequences. We will not utilize it here, obviously, yes, because length of this sequence is n multiplied by t. T is too large. We can't utilize this algorithm, yeah. But just knowledge of this algorithm will give us some ideas of how to construct algorithm for this problem. Yeah. So we will not use this algorithm, but we will use ideas from this algorithm. See, so this is why it's important to learn algorithms even if you don't use them explicitly. Yeah. So you're not only using algorithms explicitly. Sometimes you take the ideas from the algorithms to use them in other problems. Let's go. So how do you solve it here? So what will change? So again, we didn't utilize this property yet. This property, this n multiplied by max b is small. Let's think about my max b. So this max b is small. So we have small values in array in this. So we have pretty long sequence, but we have small values. Basically, okay. Let's visualize like this. So you have. Let's think of it. Let's think about it in the following terms. So, what does it mean to find longest increasing subsequence? So imagine you have so this is your so I want sorry so I have sequence. Let me show you. So I have this sequence. Yeah. So you want to find some subsequence. So you want to pick some elements. Yeah. So each element is greater than the previous one. Basically, you have two-dimensional problem. Yeah. So so imagine you have not elements, but you have a two-dimensional picture. So this is I and this is AI. Yeah. And you have some values. So you have 1, 2, 3. So this is just index. And here we have some values. Yeah. And here increasing subsequence is just a sequence of dots such they all go in right up direction. See? So if you pick some increasing subsequence, you pick some dots here such that every time you go in positive direction here. Okay. Again, it's important to think about all the classical problems from different perspectives. Yeah. So the better, okay, the more knowledge you know about classical problems, the better it will help you for some future problems. They may utilize different perspective of the same problem. For example, for increasing sequences, you also can solve it using, let's say, segment trees. So if you know how to do it, it may also help you. Yeah. So many, if you can solve, if you know multiple ways to solve the same classical problem, maybe some of them will help you in some future problems. Let's go back to our problems. Why it's important to think about like this? Because two-dimensional problems here are kind of symmetrical by these two coordinates. So we have two coordinates, and they kind of interchangeable. See? So we can not think about, we can think not in these terms, but we can just rotate this picture like this. Go AI here and go I here, and have the same picture. Yeah. So I just how it's called mirror everything by this main diagonal. You see. So I just swapped coordinates x with x and y. So we have the same picture. What is? But now this is small. Yeah. So in the initial problem, I have very long sequence with small values. Again, I try to utilize this property that I have small values. Yeah. So in the initial picture, I have a long array with small values. Here I have very short array with small values. Right? Problem is I have multiple values in the same row, but okay. Okay, now I will try to use the same algorithm as before. So I will, but in this direction. So I will go from left to right. In this way, I go from small values to large values. See? So I go from small values to large values. And maintain array D. So array D of X now. So before it was the minimal last element of the sequence of size X. Yeah. Now it will be, so now these coordinates swapped. Yeah. So my value will be this. So I will minimize this I. So it will be minimal coordinate of the last element of sequence of size X. Yeah. So it will be let's say minimal position of last element and of sequence of subsequence of size X. Yeah. So for every size, I will find the leftmost possible position of the last element of sequence of this size. Okay? And then I will update this by adding bigger and bigger element. Yeah? So I take all elements of the same value and try to add all of them and update my picture. And then update again and update. Yeah. So I take all elements of the same value and update my values of array D. Whew, hope it's clear enough. Okay, so here before I drawn the same pictures, not that different. Okay, so Okay, so what I'm doing here, yeah. So plan. So I want to add a new element. Okay, this x is different. So imagine I want to add some extra element and update array d. So how do you update array d? Again, for each let me show you. So imagine so this is array d. So now I add one extra element to my so this is my sequence. It's periodic with period n. Yeah, you want to add some extra element. Let's say element. What letter to use? Okay, let's say element a. A is my array. Okay, doesn't matter. Let's say element a. So imagine this element is the last element of the sequence of size x. What does it mean? It means I have this element, this is the last element, and before this, I have some sequence of size x minus 1. Yeah, so I can take sequence of size x minus 1 and add this element a to the end. Yes, because I'm processing all elements in increasing order, all these elements are less than mine. Yeah, so I don't need to check this. So I take any sequence of size x minus 1, add my element here, and increase it by 1. See? Okay. That's it. So now I will do it in reverse order again. Again, this problem is mostly about reversing the what you're calculating and when you calculate. So yeah. So I will take all the sequences from my array D, and for every sequence, I will find the leftmost element I can add to this sequence. So I take my sequence, find the first element equal A to the right from my end, yeah, and update sequence of size. Okay, let's say sequence X. So I find sequence of size X, take the last element, for it find the closest element with value A, and then update sequence X plus 1. That's it. To do this, you need to find the closest element to the right from your position. You can pre-calculate it. Yeah, you'll see. Okay, here I'm just reading date. It's boring. Here. I'm creating array D of size n plus 1. N plus 1 because maximal length sequence is at most n. Yeah, the sequence must be strictly increasing, so total size of the sequence can be greater than n. That's another important observation. Yes, I missed it. Sequence is strictly increasing. You can't put more than n elements in the sequence. Just stop this. Boring. Yeah. Okay. So here. Okay. So number x. So x is the value. Now here is okay. Use different names for variables here, but okay. So let's take the element x. All elements with value x. Yeah. Now for every position, I will find the closest element to the right, which is equal to x. Yeah. It's easy. You just go from right to left, yeah, and remember the last position equal x. Yeah, like this. Yeah. So for every position, I find the closest position to the right equal to x. Okay, here I just check. If I don't have elements equal to x, just continue. You don't need to update, yes, your dynamic programming if you don't have values. Okay, now I update my array D. So I look for my array D. Okay, I decided to put just infinities there. So if plus infinity means I don't have this sequence. Yeah. So di is di represents a sequence of size I of I elements. Yeah. If it is long max, it means I don't have this sequence at all. Okay, now I'm taking this sequence and try to update sequence I+1. So to do this, I need to find the closest element equal to x to the right from this position. So I do it like this. I find the block and position inside this block. So B is my index of my block, P is my position inside this block. I check if I have the next position inside the same block, yeah, then my next element will be in the same block with position next of P. Try to avoid integer overflow problems. If it is not, then my next position should be in the next block. So my next position will be first position in the next block. Yeah, I check if my block is not the last, then I can take the next block and find the first position in the next block. So I take block B+1, and the first position is Z, because Z is from here, see? So it's the leftmost position in the block. That's it. That's it. So now for di, I find the closest element to the right equal to x. Now I can update di+1 using this value. That's it. That's it. That's the whole calculation actually. Yeah. So you take array d and update all the values using the closest possible element equal to x. And now I just output the result. So I find the maximal element not equal to infinity. Maximal element not equal to infinity is the maximal of length of the increasing sequence which exists. Yeah? Okay, I'm not sure what the problem authors actually expect me to do this in this problem, but I think my solution is pretty elegant. So yeah, not that much cheating in this solution happens. So it's a pretty clear solution. Yeah. So that's it. So I will just, yeah, so it will just work from the first try, surprisingly. I would love to read your solutions for on G and H actually, but you didn't try. Sad. So again, hope someone will solve G and H later, so I will read your solutions later. Okay, that's it for today. It's problem contest 23. Thank you for watching. See you next week.